You don't need to go into outer space to find weird creatures that have a certain intelligence and are about as different from humans as it's possible to be. They're already out there, in the sea. They have 3 hearts, blue blood, and 8 arms. They use color to communicate, suction cups to grab things, and jet propulsion to move. Some of them can become almost any shape they want. To their prey, they're stealthy and murderously efficient. They're the ocean's Houdinis, the octopuses, cuttlefish, and squid. Puget Sound off Washington State. Down in these murky waters, people can run into giants. Giant Pacific octopuses, up to 30 feet long and weighing 600 pounds. These are probably the basis of the monster octopuses in the old adventure stories. Approaching divers, clasping them with their tentacles and their suckers, and holding them until they drown. Except that's not what's really happening here. This octopus is, if anything, curious about what this strange creature is. It's using its delicate sense of touch to get some clues. It can pull a mouthpiece off, but it doesn't try to keep it. When it knows what it needs to know, whatever that is, it disappears into the depths. The question we can answer, though, is what do we know about it? About all octopuses? Well, all other kinds, of course, are smaller than the giant octopus, and being soft-bodied, too, they're usually hiding. Out of the way of large fish and sea mammals. And when they do go out to hunt, they do it in camouflage. This helps, but no camouflage is perfect, and an octopus isn't the only creature in the sea to use it. A scorpion fish, and an octopus that was just too big for it. Hunting can be almost as dangerous for the octopus as for the animals it's stalking. One mortal enemy is the moray eel, which sets up ambushes. It may be hard to tell who's winning this fight, but in a sense, they both are. The eel gets an arm to eat, but the octopus will still survive intact. Small blood vessels in the stump automatically cauterize themselves, and in a couple of months, the arm will just grow back. Scientists who study octopuses sometimes simulate attacks to observe their range of defenses. A poke with a camera brings an instant spurt of ink. The cloud acts as a decoy, while the octopus takes off in the opposite direction. If that doesn't work, it tries shock tactics, turning deathly white and spewing out another smokescreen of ink. The ink, by the way, isn't just a visual weapon. It also tastes bad, and is enough in itself to put most predators off the whole idea of eating octopus. If nothing else, an octopus is flexible. Not having any bones in its body, it can change into different shapes and fit into impossible-looking places. This beer bottle, for instance. The top hardly looks big enough to get a couple of arms through, much less the whole animal. But in fact, the only limit on an octopus's ability to squeeze is the size of its solid jaw. Easy. And safe. Through no intention of their own, octopuses sometimes end up in another kind of glass container. But once in a tank, they seem to adjust all right.
See how they suck?
This giant Pacific octopus is part of the display at the Seattle Aquarium, where people can come in off the street and have the mesmerizing deep-sea experience of looking an octopus in the eye. And there is something about octopus eyes. They're roughly the same size as human eyes and seem to look right at you. They're the only thing that's remotely human-like about octopuses. Octopuses can see about as well as humans, but their main sense is touch. This octopus has more than 1,600 suckers, each as sensitive as a tongue. In each sucker's skin are 3 kinds of cells. Some feel stretch and some pressure, but most detect chemicals, which is exactly what the taste buds do. These so-called taste-sensitive cells have tufts of hair in them that waft in the water and collect telltale chemicals. Every sucker has about 10,000 taste cells, which means that every octopus arm has more than 2 million. Altogether, there are more sense cells and nerves in an octopus's body than in its brain.
See, now he's breathing.
As nervous systems go, this is seriously advanced. But octopuses are close relatives of some of the most nerveless-looking creatures in nature. The mollusks, clams, slugs, and snails. The mollusks and the octopus's squid and cuttlefish share an ancestor, a plain, pin-brained, not very spectacular limpet. 500 million years ago, the ancestral limpets made a living on the seabed, taking whatever scraps came their way. They were very slow-moving, with only their shells between them and their predators. But in time, their shells developed gas-filled chambers, and their lives gained a third dimension. They could float away from danger. 200 million years later, and the shells had been refined into lots of new shapes, spirals of all sizes from a few inches across to several feet. These were the ammonites, and the seas thronged with them. Their shells are among the most common fossils found today, but what their soft parts were like, nobody is quite sure. They probably swam like this modern creature, a nautilus. Modern, but it's been around for 450 million years, which is 100 million years longer than its ammonite cousins lasted. Powerful predators chipped away at their numbers, until climate change probably wiped them out. They left the oceans to this animal, one with tentacles for grabbing prey, and a long muscular body with a shell inside. The faster and more agile belemnite, a great uncle of all the squid. All 400 species of them, from the tiny eastern Pacific opalescent squid, just a few inches long, to bruisers such as the 6-foot Humboldt squid. Humboldts are voracious eaters that will attack almost anything they see, their skin flashing like neon signs as they feed. Squid in general are much more like fish than any of their mollusk relations, and they're more athletic than octopuses and cuttlefish. Their streamlined, torpedo-shaped bodies are almost pure muscle. They can swim as fast as some birds fly. Like an octopus, a squid has 8 arms, but for extra grip, it also has 2 long prey-grabbing tentacles. Squid also have triangular fins for balance and steering, and a remnant of the belemnite's internal shell. It's so much of a remnant, though, that there's nothing shell-like about it. A flimsy, transparent, plasticky blade that just helps to stiffen the squid's long, floppy body. The body itself is a cylinder of muscle with a hollow core because it's a jet engine. The squid sucks water in through a hole near its head, and then by clenching its muscles, pushes it out through a siphon tube. And the siphon is directional. Depending on where it's pointed, the squid can move up, down, sideways, forward, or backwards. Not all squid are jazzy swimmers, though. There's a stubby little one, for instance, named Rossia, whose fins are more like shovels than sails. And are, in fact, used for digging in the sandy bottom, where it waits to surprise passing prey. The squid's cousin, the cuttlefish, has a single long fin rippling from the back of its head to its tail. This is an excellent stabilizer and allows for underwater acrobatics. A cuttlefish can even hover motionless like a helicopter. This animal also has a structure on the inside which evolved from a shell. The porous cuttlebone keeps the animal afloat while the fin and the jet put it through its maneuvers. Octopuses don't have a shell in any shape or form, and they're not good floaters. What they are mainly is walkers. They use their arms as legs to bump along the seabed. They've still got the family jet, though, and from time to time they do use it. From a walk, an octopus can take off like Superman. The arms become rudders, and the head becomes a kind of prow. This is mainly an escape technique, usually used when the octopus needs to zip fast as a fish back to the safety of its den. Some dens, though, don't feel very safe. If, for instance, the opening is too big, the octopus does something that looks intelligent. It blocks it up. But is this intelligence? Dr. Jean Boll studies the way octopuses learn and behave.
When they go in their dens, they pull rocks and objects in front of the opening to block off and make themselves feel safer. And some people have argued that this is a sort of tool use, using objects to protect themselves, and therefore it's a sign that octopuses are intelligent. I'm not so sure that it is. Complex behavior and intelligent behavior are not quite the same thing. You can have complex behavior that's fixed, it's the same every single time, and most people would not consider that particularly intelligent. Octopuses certainly have complex behavior and have lots of different behaviors, but whether it's intelligent or not, I think remains to be seen. Most people who keep them as pets tend to think of them as very, very intelligent. They appear to look you straight in the eye, which is very endearing to human beings. They are responsive to you as the pet owner and feed them, and they come to you. And some of them, when they're accustomed to you, would even meet your finger on the glass. And they do things that we would interpret as intelligent because we would use intelligence to do them.
Intelligent or not, octopuses can do some things that seem pretty smart. Escaping from their tanks, for instance. Keeping them in isn't always easy. Because whatever their brain power, they're certainly strong. A 1-pound octopus can lift a 40-pound aquarium lid. That's like a man lifting a boxcar. And that's only the beginning of the adventure.
There's some remarkable stories about how octopuses can unscrew jars to get crabs, or there's even a story that an octopus climbs out of an aquarium, walks down the block into another aquarium to get a fish, and then comes home again. I don't think there's any actual substantiation for these stories. It's true that some octopuses can pull a rubber plug or bung out of a jar to get a crab inside. But some octopuses do it and some don't, and we don't have good evidence that they actually learn to do it.
It does take a certain skill to unplug a jar and pick out the crab inside. But catching a crab in the wild takes a lot of skill too. This, after all, is the softest of soft-bodied animals, attacking one of the hardest, with lethal claws attached. First, the octopus stalks the crab, waiting until it can pounce from behind, away from the claws. A quick leap and a grab with the suckers, and the octopus pulls the crab to its mouth at the hub of the arms. Then the octopus uses its only hard part, its parrot-like beak, to bite the crab at its only soft part, the membrane where the hard parts meet. Next, it paralyzes the crab with nerve venom, dissolves its muscle with saliva, pulls the shell open, and sucks out the liquefied flesh, leaving behind a perfectly clean plate. Octopuses will eat almost anything, and they eat a lot. Every day, an octopus gains up to 2% of its body weight, the equivalent of a human gaining 4 pounds a day. Sometimes an octopus fishes with its net, the webbing between its arms. It pounces on a piece of coral, traps all the small creatures there in the web, and then scratches around in the net to see what it's got. In their pursuit of prey, octopuses sometimes even leave the water. That doesn't mean they can breathe air, though. This Australian species, which hunts in the shallows of reefs, has to slip into pools from time to time so it can use its gills. And in or out of the water, having 8 arms means that an octopus can kill things that are larger than itself. Usually, only animals that hunt in packs can do that. So an octopus amounts to a one-animal pack. When the octopus has eaten its fill, it goes home to its den. Not as straightforward a proposition as it sounds. Because how does the octopus know where it is in relation to the den? Octopus researchers have shown that the animal recognizes landmarks. And no matter how far, wide, and meandering its foray has been, it goes home in a straight line. Which means it must have some kind of a seabed map in its head. Gene Boll tests this idea by putting octopuses in mazes and finding out if they can tell right from left.
Well, this is the maze. There are two choices. The octopus can either go to the right or to the left. The left hole is actually blocked off, although you can't tell right now, while this hole is open, and it's up to the octopus to figure out which way to go. I'll be watching the whole thing from a camera overhead, because if I stay in sight, the octopus will watch me rather than pay attention to which way to go. So here it goes. The octopus is in the house, and it will drop out now because it's out of the water. This octopus hates shallow water and it hates bright light, so it's going to try to find the open burrow. He can't see very far because he's low to the ground, so he can't tell ahead of time that that hole is blocked off. So he's exploring slowly and carefully around the outside edge. For the first time, it takes an octopus anywhere up to 10 minutes to find the open hole. But it looks like this octopus is moving quite quickly, because there he goes now. He's just found it.
That was that octopus's first trial. Each animal runs through the maze 20, 30, or 40 times. And with experience, the octopuses do get quicker. And that at least suggests learning.
We do know that they're capable of quite complex behaviors of all kinds, including spatial orientation behavior. But we don't know yet, and it's going to take a lot more experimentation to determine whether they're intelligent in the sense that we mean intelligence for ourselves.
There are several ways of judging an animal's intelligence. One is by the intricacy of its communication skills. And this animal, the cuttlefish, is a veritable Shakespeare. Except that it doesn't speak with words, but with patterns. Those stripes rippling across the back of a male cuttlefish are telling another male where to go, away. The rippler has found a female and is staking his claim. It's the cuttlefish's brain that's making it happen. It thinks the pattern onto its body. Squid and octopuses can do this too, by sending signals through nerves to what's known as chromatophores, tens of thousands of tiny color cells in the skin. Each chromatophore is like a bag of pigment at the center of spokes of muscles. When the nerves relax the muscles, the bag contracts and wrinkles into ridges and grooves. But when the muscles pull, the bag stretches out, revealing the pigments in all their glory. Basically, there are only 4 colors in the chromatophores: black, brown, red, and yellow. But the timing of their opening and closing gives the illusion of a lot more than that, of tones that may not be seen anywhere else in nature. It really is the timing that does the trick. Fractions of seconds are involved, and the effect is like neon lights traveling across the skin. The human brain can signal a change in skin color too. It's called blushing. But compared to what a cuttlefish can do, that's pretty rudimentary. The difference between a grunt and a song. Cuttlefish use this neon to send signals to each other, but they also flash at their prey. Why, though? Surely, only cuttlefish know what the signals mean. There is a theory. They're hypnotizing the intended meal, spellbinding it while the cuttlefish takes aim. Probably the most important use of the patterns for cuttlefish and octopuses is disguise. The best defense these soft-bodied animals have is hiding. Camouflage is a way of doing that and being in the open at the same time. Cuttlefish camouflage is the specialty of Dr. John Messenger.
Well, what we've got here is an animal over a gravelly bottom. He is almost uniform. Half closing your eyes, you can see something which has quite a good intensity match to the background. Now he's coming over the gravel and you're getting the white spots up very nicely. The patterning he's showing is somewhere between mottle and stipple. He's also erecting muscle in the skin, so it gives the skin a spiky appearance.
So the cuttlefish is changing its skin's color and texture. It gets that mottled effect by way of another kind of skin cell, the leucophore, which is covered in tiny white lumps. When light hits these, it's scattered and reflected back much whiter, making pale patches on the cuttlefish's skin. Sometimes the effect is geometric.
Well, here we've got an animal which is on a much more variegated background. What he's doing is now generating very bold and big patterns, squares and stripes, which completely break up the overall outline of the animal.
In really murky water, you'd have no idea what this animal was, or even that it was an animal. But how does it know what patterns to create? How does a cuttlefish see its world? John Messenger has been experimenting with colored gravel.
Well, here we've got a cuttlefish sitting on an artificial seabed, and if you look at him, you'll see that he is very pale, and it's not a bad brightness match. The eye is evidently looking down at the white stones at the bottom of the tank, not at the green wall at the side. They're always looking at the bottom. Well, we're now going to lift up this barrier and hope we can persuade this animal to move across onto a much darker background. I shall tickle him rather gently, like this, and he's beginning to move across, and I think at once you can see he's turned very dark.
One important point about this cuttlefish, it can't even see red. It's colorblind. It sees white, black, and shades of gray. But it sees them very precisely and can tell from the subtle contrasts between the grays exactly how to blend in. Sometimes, though, the contrast is a little too subtle.
Here we've got a cuttlefish on a white background with red stones. That's as you and I see it. As he sees it, he's on a white background with some very dark stone. So it isn't a uniform background, it's a patterned background. And look at the animal himself, you can see he's patterned. He's got some spots on the mantle bar across the head and other things. It's a definite pattern. He's decided that background isn't uniform. This one now, very obvious difference to us with colour vision, blue and yellow, but in fact these stones were chosen because they're intensity matched. They are the same brightness. To this colourblind animal, they are no different. They're equal sorts of grey. And so what does he do? He puts on no pattern at all. He's a rather uniform stipple, which he hopes is the best way to match what he sees as a uniform background.
But how can a colorblind animal, and octopuses are colorblind too, possibly camouflage itself against all sorts of colors in the wild? This looks like magic. An octopus disappears into the pinks and purples of a coral reef. And this looks like something from nothing. One rises out of the blues and greens of eelgrass. It's done with yet another kind of skin cell, the iridophore. Instead of generating color, iridophores contain stacks of reflective discs that act as prisms. They split the surrounding light and cover the octopus in blues and greens. The blue rings of the blue-ringed octopus are also done with iridophores, only not for camouflage. They're meant to be seen. They're a skull and crossbones, a venom warning. A 1-ounce blue-ringed octopus carries enough poison to paralyze 10 people. Squid have iridophores too, but shaped more like ribbons than discs. They also reflect and split light and give squid the silvery, bluey rings around their eyes, making them less conspicuous, the opposite of eyeliner. And the eyes are big because vision is vital to the animal, never mind the color blindness. Squid's eyes are well developed and far apart, for a wide field of view. So wide, in fact, that a squid can almost see in front and behind at the same time. And it's seldom taken in by tricks of light. That's because its eyes are fixed with something like polarizing filters. This enemy barracuda, for instance, counts on its prey losing it in the glare of the sky. This squid isn't fooled, though. The eyes adjust and sift out the rays that could cause confusion and see what they need to see in unambiguous black and white. The squid see the threat and then do something about it. They change their skin pattern and disappear against the foliage. The way squid defend themselves has been studied by Dr. Roger Hanlon.
The primary defense of squids is camouflage, and they do a masterful job of this. If they go down low near the soft corals, they can match the shape and the general color and texture of these corals very well indeed. If they're aimed up, they can put a banding pattern across the bottom that matches the bands of the gorgonian. So they can look exactly like whatever shape the gorgonian is. Predators just don't see them. When camouflage fails, that is when the predator actually sees the squid and they move close in to begin the attack sequence, squids do something totally different. They go into their secondary defense. And in this case, they may look unlike a squid by putting two false eye spots on the other side of the body so that the predator doesn't know which way they're going to jet, forward or backward. The squid may then raise its arms in a startle display that will stop the forward movement of the predator. And in that critical moment, it will then go into the next phase of secondary defense, which is to blanch ink and jet away at very rapid speed, leaving only this ink pseudomorph of a squid. And of course the predator then bites into that ink and gets no squid whatsoever and rather a bad flavor as well. It's interesting that octopuses have a similar system. That is, they have the primary defense of camouflage, which they do very well, and they have the same sequence of secondary defenses too. Here in the Caymans, we were able to study this octopus defensive behavior for the first time ever. And it was very nice indeed because we were able to act as the predators so that no harm came to the octopus, but we were still able to see the full repertoire of secondary defenses. And it came out very well indeed.
Dr. Hanlon and his team have been seeing some of these defenses for the first time ever. They video the octopuses, and at the end of each day, they play back what they've seen and go over it in detail.
Is that up on your lens?
Is that offensive?
It's right on the lens. So what happens is the animal has tried all its defensive maneuvers, and the last thing it does is go on the offense, leap on the predator or the camera. Now you can see the suckers moving right across the dome port on the lens. You never know what they're going to do next.
Wow.
Now this, I think, is a brilliant example of stealth. We call it the moving rock or the moving algae. The octopus takes up the posture and looks like a rock and moves just slowly enough not to be detected for movement, but it looks like one of the other rocks right in the picture. Meanwhile, they move away from the predator. Soon they get enough distance and they're gone.
So now we're into defensive.
This is the secondary defense. Exactly.
Okay.
Crips has
How big
failed.
is he
they take
across?
off. He's only about maybe 1 foot. Not very big animal.
Looks bigger.
So they change from camouflage to big and bright. So they look bigger than they really are. That's part of the idea, is to stop the predator.
Is that the ink that they shoot out?
Yeah, so the ink comes flying out and the predator usually takes a bite of the ink. Here's the other trick they do. There he is right there.
Boy, that's quite a difference. Such a contrast.
So that's the startle threat and then jet away and ink in your face.
It's amazing.
We want to go back to see what happened.
Sure, that'd be great.
Okay, now here is ultimate crypsis. The animal is just a part of the rock at the bottom. It's absolutely invisible. Then look at this change. Magnificent startle threat behavior and ink and jet.
And he's still inking. Lots of ink, eh?
Now this we have never seen before. This is the ultimate startle display when the animal is cornered. And it gets this face that we've never seen before. It looks like an owl or a ghost or whatever. And we think it's sort of the ultimate threat display once the predator is really in close. Looks totally unlike an octopus whatsoever. And that's the whole idea. I'm not an octopus, don't mess with me.
The signal is simple and clear and could be understood by almost any other animal. But when octopus, cuttlefish, and squid are communicating among themselves, things get complicated. Caribbean reef squid, for instance, have a very sophisticated courtship. Here, a male in the center has picked out a female and is trying to isolate her from the rest of the shoal. But by turning white, the female makes it clear that she's not ready for mating. Not yet, and not necessarily with him in particular. The whiteness is also a signal to the other males that she's still available. The male, in turn, blanches at them, but only on the side of his body that they can see and she can't. A rival male comes too close, and a fight starts. While they, in their squid way, slug it out, the female goes back to the shoal to see if she can find a better male. And the original male, having won his fight, goes after her again. At first she seems reluctant, but after all, he has won a fight and will probably have fight-winning offspring. So she accepts him, and they court, swimming fast, side by side. The actual mating is done in a blink. The male reaches out and sticks a packet of sperm on her head or arms. She then picks it up and tucks it into a storage organ near her mouth. Sperm can remain there inactive for many months. Reef squid courtship can be pretty hectic sometimes, but it's almost calm compared to another species, the opalescent squid. There's a full moon off the California coast. The opalescents gather in shoals of thousands, their translucent bodies glowing in the moonlight. All through the shoal, females are being grabbed by males, whose arms flush red as they mate with them. Once a male has a female in his clutches, he holds on tight. All around, there are unattached males who, in their frustration, will sometimes even resort to ramming a mating pair. And sometimes ramming works. Even if a female is being held for all she's worth, a ram raider can still fertilize her. In studying another species with this kind of mating system, scientists have found females laying eggs fertilized by a whole lot of different males. And there are a whole lot of eggs, up to 55,000 per mother. They're left in large communal nurseries, in capsules anchored in the sand. When the young squid hatch, there will only be other young squid around them. Having reproduced and finished their mission in life, the older generation will have died. By and large, squid, cuttlefish, and octopuses are not long-lived animals. A year is a lifetime for most of them. There's one octopus, though, that breaks the records. It's found 600 feet down in the cold, dark waters around the North Pole. It's the Arctic octopus, and it lives for 6 years. It's tiny, too, about the size of a golf ball. But in one way, it's the biggest octopus in the sea. In proportion to its body, the male has the largest sexual organ of any octopus. It's at the tip of the third right arm. No one knows for sure why it needs to be so big, and until scientists can spend more time 600 feet deep in the Arctic Ocean, they can only speculate. So far, they've only been able to study them closely in tanks, and one thing they can see is that the male doesn't waste much time with courtship. When he finds a female, he literally seizes the opportunity. What he's trying to do is put his arm inside her sac-like body cavity. This is something that's never been seen in the wild, and so any ideas about the reason for the long arm are just ideas. Maybe it anchors the male during the mating. Maybe it's a spoon for removing sperm from a previous male. Maybe it's a way of making absolutely certain that the rare encounters between these octopuses are successful. Whatever, this male finally does succeed. He deposits a small sac of sperm and withdraws. For her part, the female, having gotten the precious sperm, will now store it for about 5 months while her eggs develop. The story of every mother octopus is the ultimate in maternal devotion. Off the North American west coast, a giant Pacific octopus is cloistered in her den, tending her eggs. Several months ago, she laid between 10 and 20,000 of them, and she hasn't left the den since, not even to eat. The eggs hang overhead like great bunches of grapes, and she tends them, aerating them with bursts from her jet. And stroking them with her arms to remove algae. Inside the eggs are yolk sacs, which are food for the larvae during the 6 months before they hatch. What the mother lives on are her own internal tissues. As she broods the eggs, she digests herself, and by the time they hatch, she has wasted away. The babies go into the world with no further assistance. Giant octopuses are big, but nothing like the legendary monsters that could drag whole ships under. This probably never happened, but that doesn't mean there aren't giant squids in the sea. Dr. Clyde Roper has studied the evidence.
While many aspects of the giant squid still are very mysterious, they are no longer animals of mythology. And the reason is because we now have a number of specimens. The point is, we have never seen a live giant squid. What we know is from specimens that have been washed ashore, stranded on beaches from the stomachs of their major predator, sperm whales, and also from fishermen's nets. It's like detective work, trying to put together little bits of information to learn about the giant squid. When we have these bits of information, we can put them together and make a model of a giant squid, such as this one in the Houston Museum of Natural Science. Giant squids truly are gigantic, huge animals. For example, the largest ever measured from tip of tail to tip of the tentacles is about 18 meters in total length. That's the length between the pitcher's mound and home plate on a baseball field. And the largest ones would weigh 1,000, perhaps even 2,000 pounds. We know enough now about their anatomy to understand that they're not such powerful creatures that they could destroy a submarine as the one in Jules Verne, 20,000 Leagues Under the Sea, almost did. Their eyes are really fascinating. They are the largest eyes in the animal kingdom, about the size of a volleyball. The reason is that these animals are deep-sea animals. They live very deep, from 200 meters down to perhaps 1,000 or even more. The only light down at those depths comes from other animals that produce light. Flashes and glows, these large eyes gather in the light, and the animal uses that to gather and capture their prey.
Since no one has ever seen a live giant squid, we can only imagine what they look like as they cruise the depths in search of food. People used to think giant squid attacked sperm whales because these deep divers were often found with big sucker marks on their mouths and heads. But analysis of the whale's stomach contents eventually revealed the reverse. They were eating the squid. But what actually does happen? The only way to find out is to go down and look. Scientists would have done this before, but only lately has there been the technology to explore the deepest parts of the ocean. A descent into a parallel planet Earth, unknown, unexplored, and absolutely dark. But there are more species of octopus and squid down here than there are in shallow waters. The cockatoo squid, whose way of holding its arms above its head makes it look like a parrot with a crest. A squid with long, ropey tentacles, which it uses as fishing lines. 7,500 feet down, and two ghostly white octopuses, a little one sitting on the head of a big one. Two different species? Or maybe a tiny male and an enormous female mating? No one knows yet. They've only just been seen.
Piggybacking octopuses. Mom and baby, is that kind of could be?
Deeper still, 9,000 feet. The cirrate octopus. It has paddle-like fins and arms that have turned into the ribs of an umbrella. It parachutes across the seabed on some mystery mission. Posturing, perhaps, or maybe collecting food in its net. Since there's no way for people to get out of these submarines and investigate the deep-sea animals firsthand, contact with them is a little blunt, but sometimes good enough. What does a cirrate octopus do when it's attacked? It sucks water into its net, touches the tips of its arms together, and turns into something like a pumpkin. A predator, at the very least, would be confused. light from the sun ever reaches these ocean depths. And yet many of the creatures here do have eyes and use sight. That's because many of these creatures, including a lot of the squid, generate light of their own. Firefly squid. They live at a relatively shallow 1,200 feet, where there's still a slight glow from above. To disguise their silhouettes against this, they produce sparkling blue light. And when they spawn, they go near the surface, where they're commonly caught by fishermen. The blue flashes come from the tips of each squid's arms and could conceivably blind an attacker while the squid got away. Firefly squid are one of 700 species of squid, cuttlefish, and octopus that are known to exist. How many do exist is, of course, unknown, and only 100 of the known species have ever been seen alive. There's a lot left to discover about both the ones we don't know and the ones we do. These creatures are so unlike humans that sometimes you have to wonder how we could both inhabit the same planet. There's a fascinating journey ahead for those who follow these alien animals into their undersea world.